Today's lesson is called Average Rate of Change. So to start out, I want you to try the opening exercise. It says find the rate of change of each representation. So you have a graph, a table, and two coordinates. So at this time, please pause the video, try to find the rate of change for each of these representations, and then resume the video to go over your answers. Okay, so finding the rate of change is the same thing or similar to finding the slope. So you should have background and experience with finding the slope due to your previous coursework. Looking at A, we want to pick any 2 points on the graph, and we want to count the rise over the run. So with the two coordinates that I picked, I had to go down 3 and to the right 4. So that's -3/4 as our slope or rate of change. For a table of values in the middle, you want to find your change in Y and put that over your change in X. So remember that little triangle symbol stands for change. So you're basically subtracting your Y's, subtracting your X's. So from 10 to 8, it went down 2. From -4 to 0, it went up 4. So that means you have -2/4 or a slope or rate of change of -1/2. Between the two coordinates, we want to use the slope formula. So that's y2 minus y1 over x2 minus x1. I would highly suggest that you take the time to label your coordinates. So the way that we label them is we know in a coordinate x is first, y is second. The little subscripts are showing you that there are two different coordinates. So x1 is x from the first coordinate, y1 is y from the first coordinate, x2 is x from the second coordinate, and y2 is y from the second coordinate. So my second suggestion, you can kind of see by my color coding, I would suggest you make the outline of the formula and then fill in your missing values so that you don't drop any negatives. Because as you can see on the bottom of the fraction, we would have had 6, a subtraction symbol from the formula, but then we also have a value that is -6, which leads to double negatives, which means we're actually adding. So you get -4/12 or -1/3. So now that we've gone over and reviewed the opening exercise and how to find the rate of change for those different representations, we want to look at our big idea for today. Functions are rules that give us outputs when we supply them with inputs. And you know we've been working on that this chapter. We often want to know how fast the outputs are changing compared to a change in the input values. This is referred to as the average rate of change of a function. When working with functions of all types, the average rate of change is expressed using function notation. So it says average rate of change. For the function y equals f of x, the average rate of change, or average rate that f of x changes from x equals a to x equals b, is given by this formula. So you're going to find the f of the b value. So f of b, you're going to find f of a, and then you're going to put that over the b value minus the a value, which essentially is the same thing as change in y over change in x, which is how much the y values change compared to how much the x values changed, which really, even though this looks a little bit different, as you can see underneath, it says, while this new formula may look strange, it is really just a rewrite of y2 minus y1 and x2 minus x1. So very similar to the slope formula, but with our new function notation, since we are talking about functions and average rate of change. Okay, so we're going to look at example 1 together. Given the functions g of x, f of x, and h of x shown, we're going to list the functions from from greatest to least by average rate of change over the interval 0 is less than x is less than 3. So looking at that formula we have up above, we know we need to find the function's value at these different values. So we have to find f of b and f of a. So we're going to use our domain of 0 is less than x is less than or 0 is less than or equal to x less than or equal to 3 to give us our two critical values. So for the function g, we need to find g of 0. So we're going to put 0 in x's spot. 0 squared is 0, minus 2 times 0 is all overall going to be 0. And then we're going to also find g of 3. Remember, anytime we are doing substitution, we want to make sure we put it in parentheses. So 3 squared is 9. Negative 2 times 3 would be minus 6, which means we have a value of 3. So when we look at the formula above, the function's name was f. Here our function's name is g. So we're going to do g of the b value minus g of the a value all over b minus a. So you want to do basically that second value first. So you want to do g of 3, which is 3, minus g of a, which was 0, over the actual b value. So that was what was in the input part, right? So 3 minus 0 again. So that would be 3 over 3, which is 1. So the average rate of change for g of x is 1. So now in the center, we have a table of values. We're going to treat that very similar. We are going to find the 2 critical points. Here the function's name is f. So we're going to do f of 0, which in the table corresponds to 1. The input of 0 gives an output of 1. And then f of 3, an input of 3 gives an output of 7. So now that formula that we had over there, now with f's, so f of b minus f of a all over b minus a would be equal to f of b, which would be the f of 3, was 7, minus f of a, which would be the f of 0, which is 1, would be over b minus a, which was 3 minus 0. So 7 take away 1 gives us 6 over 3. And then we see that this has an average rate of change of 2. And then lastly, we have a graph. So we're going over all the representations in this one question. I'm going to find the 2 critical points I need, f of 0. Here it's h of 0 though, because we have a function of h. So h of 0 is equal to, so an input of 0 looks like it has an output of 2 because this coordinate is 0, 2. So h of 0 would be 2. And then an input of 3 has an output of 9. So 3, 9. So we are going to write h of 3 equals 9. So then we will do our new formula with h's. So h of b minus h of a over b minus a would be, h of b was 9, h of a was 2, and then b minus a would still be 3 minus 0. So 9 take away 2 is 7 over 3, which gives us 7/3, which you could leave it like that, or you can make that into 2 1/3. And then remember, we want to go from greatest to least. So my greatest rate of change was 2 1/3. So that's h of x. Then it would be 2 for the table, so that was f of x. And then that would be 1 for the equation, so that is g of x. So that is the order of my functions from greatest to least. So now going on to our next question. Average rate of change often informs us about how fast something is happening over an interval of time. Keep in mind that the answers to all of these applied problems end up being a rate with per units attached. So we have to be really careful about how we label our answers. So in example 2, the Jameson family kept a log of the distance they traveled during a trip, as represented by the graph below. During which interval was their average speed the greatest? Calculate the average speed in miles per hour for each. So as you can see, this is not linear. This isn't a constant rate of change, and you could even tell that with these back here. That's why we're finding the average rate of change. We're just finding it for particular intervals. So the first one wants us to go from hour 1, the first hour, to the second hour. So we have to find d of 1, and we also have to find d of 2. So in the first hour, if we look at the graph, the coordinate 140, an input of 1 had an output of 40. D of 2, an input of 2 had an output of 110. So then we will use our formula, d of b minus d of a over b minus a. So d of b was the 110 D of A was the 40. And then B minus A would be 2 minus 1. So 110 minus 40 is 70. 2 minus 1 is 1. So this is giving us 70. And then if you look, it's hours and miles. So we want to make sure we label this as miles per hour. That's important to have those units. So B wants us to go from the second hour to the fourth hour. So we're going to find D of 2. And we're also going to find D of 4. So D of 2 is 110. We knew that from before. D of 4, the input of 4 has an output of 180. So using our same formula up above, D of B minus D of A over B minus A, we get 180 minus 110 over, this time, 4 minus 2. So 180 take away 110 is 70. 4 take away 2 is 2. So that's 35 miles per hour in that portion of the trip. The next one is the 6th to the 8th hour. And just so we have good examples in our notes, I want to make a little note about this one. Remember, you can also use the slope formula. We are on a graph here. So if you wanted to, you could write down the two coordinates. So 6 hour was 6, 230. The 8th hour was 8, 350. And then you can use the slope formula, which is y2 minus y1 over x2 minus x1. Remember, it's just basically a rewrite of the slope formula using function notation. So this will be a good time for me to demonstrate the slope formula for you. I would go and label my points x and y. But I know that this first coordinate needs little subscripts of 1 because they're the x and y from the first coordinate. And then the second coordinate needs little subscripts of 2. And then my next suggestion would be to do the outline of the formula. So that way you have your subtraction from the formula and then you can plug your numbers in. So we've got y2 value of 350, y1 is 230, x2 is 8, x1 is 6. So when we find these, 350 take away 230 is 120. 8 take away 6 is 2. So we end up with 60 miles per hour. And then we need to make sure we go back and actually answer the question. During which interval was their average speed the greatest? So out of all of those, it was the greatest from the first to the second hour. Now, along with this idea of average rate of change, the other big idea of our lesson here is the main idea in dimensional analysis is to create a conversion ratio, which has the units you want in the numerator and the units you already have in the denominator. It may be necessary to multiply by more than one conversion ratio in more difficult problems. Remember that you are setting up for one or more of the units to cancel. That's the really big idea here when we work on these dimensional analysis problems, which is basically you're going to have a bunch of ratios that are converting different things into different measurements. You want to make sure you end up with the measurements that you want. So you have to set up your fractions in a way that you can cancel out all the things you don't want and keep all the things that you need. So it says Peyton is a sprinter who can run the 40-yard dash in 4.5 seconds. Convert his speed into miles per hour. So miles per hour. And they want that to the nearest tenth. So our goal here, nice to take a second to write down the goal. We want miles on top. And we want hour on the bottom. What we currently have is a 40-yard dash, so 40 yards in 4.5 seconds. So that would be 4.5 seconds. So when we're setting up our ratios, we want to think about the units that we're trying to cancel out. You can start with either the yards or the seconds. So I'm going to look at seconds. I don't want seconds to be there. So I know I'm going to need a fraction that has seconds in top so that eventually I can cross seconds right out because of canceling. And I want to eventually get these to hours. So if I'm thinking about that in my head, I've got to get seconds to minutes and then minutes to hours. So seconds first. How many seconds are in a minute? 60. So this would be 60 seconds in 1 minute. Because then I know my seconds will cancel out. And now I'm at minutes, but I'm going to need to end up at hours. So I'm going to need those minutes to cancel. So I'm going to make another fraction and make minutes on top, because then I know minutes and minutes will cancel. So I'm trying to get to hours. How many minutes are there in an hour? There are 60 minutes in 1 hour. So now I'm all set with my time because I know my seconds will cancel, my minutes will cancel, and I'll have hours left. What I still have an issue with are yards. I have yards and I need miles. So there is a conversion for this that you can reference, I believe, on the top of your reference sheet. So yards is currently on top and we want it to cancel out. So I'm going to have to put yards on the bottom. And I want them to turn into miles. So miles will be on top. And if I look at my conversion, there are 1,760 yards in 1 mile. So now I think I've set all my ratios up so that everything will cancel. That's what we'll do next. So seconds cancel with seconds, wiped out. Minutes cancel with minutes, wiped out. Yards here and yards here cancel. And so I'm left with hour and miles like I wanted. So all I have to do is take all those numbers and find out what they are. So on top, I have 40 times 60 times 60, and then obviously times 1, but I don't need to write times 1, and that's going to be miles. And then on the bottom, I have 4.5 times 1,760 times 1, which again, I don't need. And then I have hours on the bottom. So now all we have to do is take our calculators and do that math. We get 144,000 miles on top, and we get 7,920 hours on the bottom, which means our answer comes out to be 18.2 miles per hour. And that's our final answer. So this is related to the topic of average rate of change. So at this point, I would like you to try the practice questions. You're going to pause the video, try the practice on your own, and then resume the video to go over the answers. Okay, so now that you've tried on your own, let's go over the answers. Number 1, a manager wanted to analyze the online shoe sale for his business. He collected data for the number of pairs of shoes and sold each hour over a 14-hour time period. He created a graph to model the data as shown below. So that's what the picture that you're looking at. So we see time and hours on the x-axis. So that's really the t-axis here. And on the y-axis, we actually see it labeled with P of t, which is the number of pairs of shoes sold in the previous hour. So A, the manager believed the set of integers would be the most appropriate domain for this model. Explain why he is incorrect. Well, integers would include negative numbers, and we're dealing with time and the numbers of pairs of shoes, which cannot be negative. So that's why the manager is incorrect. B, state the interval for which the number of pairs of shoes sold is increasing. So you can see I highlighted that word in blue, and I highlighted the part of the graph where as t is increasing, P of t is also increasing. So that's going to happen for domain values of 0, less than or t, less than or 6. So using a t instead of x here because t is our domain, input is time and hours. So from an x value, we usually have of 0 would be a t value of 0 to a t value of 6. In part C, determine the average rate of change between the 6th and 14th hours. So we had to find P of 6 and P of 14. So when you look at the graph, P of 6, an input of 6 hours yields 120 pairs. And then an input of 14 hours yields 0 pairs. So that's 120 and 0. You make sure you do P of B first and then P of A. So that'd be 0 minus 120 over 14 minus 6. That gives us negative 120 over 8, which is negative 15. So the number of pairs of shoes decreased 15 pairs per hour on average. And it's said to explain what it means in context of the problem. So notice I'm not just saying it's negative because it's going down. I'm being very specific about the pieces of the problem, referencing the pairs of shoes and referencing why that is negative in context. And then in number 2, it's completely separate. The following conversion was done correctly. What were the final units for this conversion? So remember, you can cross cancel anything that is matching units. So I had miles in top and bottom, they canceled. Hours in top and bottom canceled. Feet and foot in top and bottom canceled, which left us with minutes and inches. And they didn't want us to actually calculate. They just wanted to know what were the final units. So our final units now, what's left over, would be inches per minute. And that concludes your lesson on average rate of change.